Hello everyone, my name is Chizhi. Today I will give a presentation about our paper to you on behalf of our research team. Today's presentation will be divided into 5 parts as the headings shown. First, I'll talk about some backgrounds of prefetchers. Memory wall is a famous obstacle laying in the way of architecture research. To address this issue, many techniques have been proposed. Prefetching is one of the classic methods. A prefetcher is a supplemental component in the CPU that can predict future memory access and prefetch data by learning memory access patterns from history, so that stores caused by some long loads can be eliminated as the picture shows. Prefetchers are widely used in high-performance CPUs because they are low overhead compared with straightly increasing cache sizes for achieving higher performance. There are many kinds of prefetchers. I focus on prefetchers that learn special correlations between memory accesses. The storage format of patterns is important for the performance of prefetchers. There are many formats used by prefetchers for storing complex access patterns. One of these formats is delta sequences. We say a delta is a difference between the current address and the last address in a region, for example in a page, and a delta sequence consists of many different deltas. Patterns described by delta sequences can be shared between pages, and the common parts of different patterns can also be shared. Besides, delta sequences store the spatial information and access order of memory accesses simultaneously. For delta sequences, there is a special predicting strategy, named recursive look-ahead. The main idea of recursive look-ahead is to recursively calculate the next delta sequence based on previous sequences to reconstruct a complete pattern. There are 3 motivations of our paper. To design a low overhead and a powerful prefetcher, we first explore the ideal coverage and the ideal accuracy that a prefetcher based on delta sequences can reach. We use the aberrant branch number to indicate the ideal accuracy. We say a delta sequence has a branch if its longest prefix is the exact prefix of some other sequences. We analyze these 2 metrics of 45 memory-intensive trances captured from the spec 2017 and draw 8 box pictures as illustrated. According to the quantitative analysis, we can reduce the branches of accessing sequences significantly by increasing the length of delta sequences to more than 3 deltas. It is more challenging to find a suitable length providing high ideal coverage in all workloads. Therefore, we believe it is a good choice for prefetchers to capture complex patterns using variable length delta sequences and supporting multiple matching. In recent years, Chefgoes, etc. have proposed VLDP that attempts to predict patterns by matching the current access sequences with multiple delta sequences of different lengths. They did not make judgments through quantitative analysis, but intuitively believe that multiple matching is better, so their design has several problems. We focus on the efficiency of different storage forms in this slide. VLDP uses multiple prediction tables to store variable length delta sequences. We think it is possible to coalesce delta sequences of variable lengths into a single table because shorter sequences are subsequences of longer ones. So the ideal form is just like the right figure. If we find a method to coalesce all these sequences into the fixed length form, it is more efficient. The last motivation is that we have observed that only a small part of deltas reappear frequently. The top 20 high-frequency deltas account for 74% of the total occurrences. Therefore, we attempt to save storage by only storing the most frequent part of access history. Next, we will show the design of our paper. In the motivation, we mentioned that it can be more efficient if we can coalesce variable length sequences into fixed length sequences, but how to make it? To improve prefetch accuracy, The repeat times of delta sequence are usually recorded, and we call it confidence. So all the sequences in the figure have their confidences. How to deal with these confidences when coalescing subsequences into one sequence? Should we keep all of them? The answer is no. Only the confidence of the longest sequence after coalescing is reserving. On the one hand, if the short sequence always reoccurrences in the same sequence, its confidence is simply the same as the sequence containing it. On the other hand, if the short sequence reoccurrences more frequently than the sequence containing it, like reappearing with various deltas, there must be multiple entries containing the short sequence that each records a portion of its confidence. So it's okay to just store only one confidence for a coalesced sequence because we can restore confidences of subsequences from all the sequences containing them. What's more, after coalescing, the sequences are reversed so that they can be allocated in the same set if they have the same recent deltas. This trick is kind of like a hash function for indexing. To only maintain high-frequency records, we attempt to dynamically map a record to an index at running time by explicitly storing its signature extended with the confidence field. The mapping relations are stored in an isolated for-associative structure in which one with the lowest confidence will be evicted during the learning phase. The delta mapping array, or DMA, keeps the mapping relations between deltas and the indexes of sets, and the delta sequences subtable, or DSS, keeps the following sequences in associated sets. In other words, the matching DMA weight number is used as a set number to DSS. Our key idea for accurate voting is to both consider the confidences of the short and long sequence matches, but with different ways to adaptively fit the lengths of matched sequences. Because we can restore the confidence of a short sequence by accumulating the confidences of entries containing it, any delta can be selected if its score, which is the sum of products of the confidences of matched sequences and the corresponding weights, satisfies the Prefetcher criteria. Due to the time limit, please check out our paper for more information of the design. In this section, we will show more elaborated examples. As illustrated, the training process is divided into 3 steps. First, the current delta sequence is assembled by these 3 operations. Second, the first delta 24 is the signature, which hits weight 2 of DMA. Then the confidence of weight 2 increases by 1, and the corresponding set 2 of DSS will be updated. Third, weight 0 of set 2 in DSS is hit by the following sequence 22, 20, 26, where the confidence of the matched entry increases by 1. If the following sequence misses in DSS, then the entry with the lowest score in set 2 will be replaced. The prefetching phase is also divided into 3 steps. First, the current delta sequence 26, 24, 22 is assembled with records. The newest delta 26 is used as the signature to locate the entry in DMA. Second, delta 26 hits in weight 3, then 24, 22, and 24 are used to match the corresponding prefixes of the records in set 3 of DSS, as shown in the figure. The delta 28 and 24 are selected at weight 0 and weight 1 of set 3. Third, the Matryoshka applies the adaptive voting strategy in our configuration. Then the best delta 28 is selected to prefetch. In the following section, we will show more detail about evaluation. We use the champion simulator to simulate 5 prefetchers, including Matryoshka. We use 2 types of benchmarks, and we expand VLDP storage capacity to 48 kilobytes to catch up with the performance of recent prefetchers. Matryoshka yields the best speed up of 53.1% over the non-prefetching baseline system. which is an improvement of 6.5% over IPCP. Compared with other prefetchers, it also achieved the highest average coverage and the lowest average over-prediction rate. In the 4-core system, Matryoshka offers a 22.2% speed up over the baseline, which is the best among these 5 prefetchers. Compared with the other 4 prefetchers, Matryoshka still obtains best performance in different configurations of the CAS system. This figure shows the performance of 5 prefetchers with either lower memory bandwidth or smaller LLC. The default configuration is 2 MB LLC and 3200 MT per second of bandwidth. Let's make a brief conclusion of our paper. First, we proposed an efficient multiple matching mechanism based on Coalesced delta sequences with only one pattern table, which reduced the storage overhead and simplified the pattern recording process. Second, in company with the multiple matching mechanism based on Coalesced delta sequences, we devised an adaptive voting strategy to fill out irrelevant prefetch candidates. Additionally, we propose a novel dynamic indexing strategy to maintain high-frequency portions of metadata and implement architecture at the storage cost of nearly 1.79 kilobytes. That is all of my presentation. Thank you very much. If you have any questions, I'm happy to answer them.